Hello everyone. Our topic of discussion was adsorption and I am on my third lecture today. So the subtopic of discussion is Langmuir Adsorption Isotherm. So we have already learned the Freundlich Adsorption Isotherm, where it has been found that the isotherm has been made on the basis of the experimental observations. Later, Langmuir made the theoretical explanation quantitatively of those experimental results. In 1916, he made some assumptions on the basis of which some mathematical formulations were done and formula or the Langmuir isotherm was obtained, which well explained the Freundlich Adsorption Isotherm. So, the Freundlich Adsorption Isotherm earlier was based on experimental observations, but the quantitative theoretical explanation was made by Langmuir in 1916, and this theory was made on some assumptions. And as for example, he took the solid gas adsorption phenomenon. There are so many other adsorption phenomena, but here only gases are adsorbed on solid surface. He took this type of instance and made the assumptions. So what were the assumptions made by Langmuir? The first assumption was the adsorbed gas behave ideally in the vapor phase. That means before adsorption, the gases were actually behaving ideally. That means they did not have any, or they do not have any interaction. So before adsorption, when the adsorbates are in the gaseous phase, they do not have, or they do not involve any kind of interaction. That means they behave ideally. When they are adsorbed, after adsorption, they are coexisting with each other on the surface of the adsorbent. Now after adsorption also, they are not making any kind of interaction with each other. That means there is no interaction between the adsorbed molecules. The third assumption was that the solid surface on which adsorption process is going on, so the adsorbing sites, that means on which the molecules getting adsorbed, those part of the surface are called the adsorption sites. So these sites are equally distant. That means they are homogeneously distributed. The solid surface is homogeneous and has a fixed number of adsorption sites. As for example, this is a schematic diagram of a solid surface made on the assumption of Langmuir. So you find here the red dots. Red dots are the adsorbing sites. Overall, this sheet is the surface, but all the parts of the surface are not able to adsorb the molecules. Only these red dots are able to adsorb. So there are 5 into 5, total 25 number of sites, out of which 4 are blue dots. That means 4 has been occupied by adsorption, and out of 25, 21 has been left bare. That means they are still available for adsorption. But the fact is that the adsorbing sites, that means these red dots, are equally distant. That means they are homogeneously distributed. The fourth assumption made by Langmuir was each site cannot adsorb more than one molecule, that is only monolayer is formed. Look at the previous picture here. In the 25 number of sites, only 25 molecules can be adsorbed, and not 26 or not more than that. That means only a single layer or a monolayer is formed over this surface. And later you will learn one more theory, which is the BET adsorption isotherm, Brunauer, Emmett, Taylor, after the name of the inventors. This is known as the BET adsorption isotherm, where multi-layer formation has been considered. But Langmuir made only consideration of a single layer formation, that means formation of a monolayer. So BET is not our topic today. Our next class, BET will be discussed. But right now we are on Langmuir Adsorption Isotherm, and its fourth assumption is each site cannot adsorb more than one molecule, that is only monolayer is formed. And in the fifth assumption, it is said that the rate of adsorption is equal to the rate of desorption, and this is the adsorption equilibrium. Okay. So adsorption is considered as an equilibrium between condensation. Condensation means adsorption of the adsorbate molecules on the adsorbent, and their desorption. Desorption means evaporation. That means getting detached from the surface. Therefore, the rate of adsorption, that means condensation, and the rate of desorption, that means evaporation, eventually becomes equal at equilibrium. Here S is the surface of the adsorbent site and A is the adsorbate molecule. So they are combining with each other. That means this is getting attached on the surface or adsorbing site, and this moiety has been formed. So it has a particular rate, and the rate constant is K adsorption, that means Ka. And the reverse process is cleavage of this moiety and desorption, that means evaporation, which is following the kinetics having rate constant Kd. So when these both rates become equal, then equilibrium has been established, and at that moment Ka becomes equal to Kd. Now let's make the mathematical formulation on the basis of these assumptions. Okay. So in the previous picture we have seen that there are 25 adsorbing sites. So 25 is the available number of sites. This is taken as a whole 1. Here in this picture there are total 13 number of sites. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. Okay. So 13 number of sites are available here. So this 13 as a whole is taken to be 1. In the previous picture 25 was taken to be 1, here 13 is taken to be 1. Now out of which the first site has been occupied, then second, third, fourth, fifth, 7th, 8th, 9th and 10th sites have been occupied. So total number of occupied sites is 7. So bare sites, that means unoccupied sites, is 6. So what is the fraction of occupation and unoccupation? The fraction of occupation is 7 out of 13, so 7 by 13, and 6 out of 13 that means 6 by 13. So this is called theta. This fraction is called theta, and this fraction is called 1 minus theta, and the total theta plus 1 minus theta is 1, that means equal to overall number of available sites. In the previous picture the theta value is 4 by 25, 1 minus theta value is 21 by 25, and theta and 1 means 25. Okay. So theta is the fraction of the total surface occupied by gas molecules at any instance. And what is 1 minus theta? 1 minus theta is the fraction of the bare surface that are available for adsorption. So the rate of adsorption should depend on the occupied site. That means how much site is getting occupied, the rate of evaporation becomes greater. So the rate of evaporation or the desorption depends on the fraction of the site which has been occupied. So it is directly proportional to theta. If 1 minus theta number of site is available for adsorption, then the rate of condensation should be proportional to 1 minus theta. So the rate of condensation or rate of adsorption is proportional to 1 minus theta. But along with that, the rate of adsorption depends upon one more factor, which is the pressure. So it is also proportional to pressure, where P is the pressure of the gas. So if this is a proportionality relationship, so this proportionality relationship can be converted into an equation. So the rate of evaporation should be equal to some constant into theta, and rate of condensation or adsorption should be equal to some constant into 1 minus theta into P. And these proportionality constants are CD and CA. Ct is the proportionality constant for desorption and Ca is the proportionality constant for adsorption, and the corresponding equations are Cd into theta for desorption and Ca into 1 minus theta into P for adsorption. Now when the equilibrium is established, then the rate of adsorption is equal to the rate of desorption. So these two terms should be equal when the process would acquire equilibrium. So this is the equation. Okay. Now if this equation is solved, then the value of theta is obtained, which is CAP by CD plus CA into P. If you divide both the numerator and the denominator by CD, then this form is obtained, and finally Ca by CD is given another form B, which is yet another constant. So both Ca and CD are constants, so B is also a constant, which is known as the adsorption coefficient, and this is equation 1. Now what is the amount of gas that is adsorbed? This is X gram of gas has been adsorbed by what is the amount of adsorbent? This amount is M. So the ratio X by M is taken to be Y, and this Y must be proportional to the fraction of the surface covered, that is the theta value. So Y is proportional to theta. Okay, here you find Y is proportional to theta, and the proportionality sign has been replaced by the equal sign with a constant, proportionality constant K. Now put the value of theta from equation 1. So what was the value of theta? In equation 1 it was Bp over 1 by B plus P, 1 plus Bp. Now K is a constant, B is another constant. So let us merge these two constants, and this is written as A. Okay, so A becomes yet another constant. So the form of this equation is Y equal to AP by 1 plus Bp. Now rearrange this equation. It is P over Y. So this becomes 1 plus Bp by A, and eventually it becomes 1 by A plus B by A into P. This is equation 2, and this is the Langmuir adsorption isotherm. Equation 2 is the mathematical form of the Langmuir adsorption isotherm, which can be converged into the Freundlich adsorption isotherm by taking some special cases. And this equation also successfully explain the curve of the adsorption isotherm from the Freundlich equation. So now we have to plot P by Y against P. So what would we get? We should get a straight line which has a slope 1 by A and which has a slope B by A and intercept 1 by A. Let's look the graph. Let's look at the graph. The graph P by Y is plotted against P. So here 1 by A is the intercept and the slope is B by A. So equation 2 is the final form of the Langmuir adsorption isotherm. Now let us consider the special cases. This is equation 2 on the top. Now when the situation is at the beginning, the pressure is very low, so P is very much less than 1, so Bp is also very much less than 1. So what should be the form of equation 2? Equation 2 takes the form, this part being very small becomes negligible, so we have only P by Y equal to 1 by A. That means Y equal to P into A. So this is equation, special form of equation 2, which is equation 2A. This is valid for adsorption at low pressure, and this one gives this form Y versus P. That means the rate of adsorption is directly proportional to the pressure of the gas. Now the special case number 2, where it is in the high pressure region. So at very high pressure, P is very much greater than 1. As a result, Bp is also very much greater than 1. So in comparison to this 1 by A part becomes negligible. So what is the form that equation takes? The form that equation takes is P by Y is equal to B by A into P. So P in the left hand side and P in the right hand side cancel each other. So we get 1 by y equal to b by a. That means y equal to a by b. This is equation 2b. Okay, so this is at very high pressure, and this equation is most significant because at high pressure the limiting pressure P0 is reached, where with increase in pressure no increase in the value of y and the curve becomes flattened. That means it becomes parallel to the x-axis and also independent of pressure. So according to equation 2b, that means for high pressure conditions y is independent of pressure and thus becomes a constant, and here adsorption reaches its limiting value. That means P0 value is reached, and at this moment no surface is left bare. That means nothing is left available for further adsorption. That means the whole surface is covered by a monolayer. Now we have considered case 1 and case 2 at very low pressure and at very high pressure. Now what should be the case in between them? This is case 3. So at intermediate pressure, equation 2 may be written as this form: y equal to kp to the power n, while n lies between 0 and 1. This is equation 2c. Now you would ask how this is becoming this equation 2c. Actually, this is an exponential relationship which is actually this equation. This equation can be written as this. You need not make any kind of derivation from here to here. Okay. Actually, you go to plot the graph where you plot y against p in equation 2, and in equation 2c you will get the same graph. That means equation 2c and 2 is same. The condition, only condition is n should have the value between 0 and 1. And this is nothing but the Freundlich isotherm. So this way the Langmuir isotherm, from its theoretical consideration, can well explain the Freundlich isotherm. So this here the Langmuir and Freundlich has been explained with each other. So we have got 3 special forms: equation 2a, 2b and 2c. Low pressure, high pressure and intermediate pressure. So equation 2a explains the initial steepness of the curve. We shall take the curve here. This is the initial steepness. This is something a straight line. So equation 2a is satisfied here, this portion only. And at high pressure this becomes parallel to the x-axis, that means becomes constant. This is equation 2b, and 2c is the intermediate pressure, where the curvature has been well explained and the Freundlich isotherm has also been validated. This way the Langmuir isotherm is very much successful to some extent in explaining the Freundlich isotherm. But there are some drawbacks, as we have explained, and due to that the BET adsorption isotherm had been required. So that's all for today. Thank you.